When you open Gauss View, you'll see a gray window that shows the molecule fragments you'll add to your structure. And the purple window will show the whole molecule you're working on. Clicking on View and then Builder will pull up a toolbar with the building tools that you can use to start building your molecule. The element fragment lets you add a specific element to your molecule. A periodic table will appear on the screen and you can choose between different elements to add. The ring icon will let you create different ring structures, like benzene. You can also manipulate your molecule using the different mouse buttons. A left click will let you rotate about the center of the molecule. Scrolling the mouse will zoom in and out. A middle click will translate the molecule in the plane. A right click will zoom and rotate simultaneously. Clicking on the center button will center the molecule in the screen. You can use the Modify Bond tool to change bond types. After clicking on any two adjacent atoms, you can change the bond type as well as the bond distance. Similarly, you can select the Modify Angle tool and choose any three atoms to adjust the bond angle. The Modify Dihedral Angle tool will let you adjust the dihedral angle between any four atoms. This angle is most often associated with Newman projections. Selecting the Delete tool will erase any atom you choose. The Add Valence tool will add hydrogen atoms to the atom you select. At any point, if you make a mistake, you can undo by typing Ctrl-Z. Once you've finished building your molecule, save it as a .gjf file. This will be the file we will later optimize using Gaussian. Let's go over these tools again using a specific example. In the bottom left corner, we have our molecule, which we'll call DCO1. We can start by selecting a benzene ring from the Ring tool. We can then use the Element tool to add the two chlorines and the nitrogen to the ring. We'll add another benzene ring to the nitrogen we just attached. Before we add the carboxylic acid group, we need to select a tetrahedral carbon from the Element tool. Once we've created a CH2 unit, we can add the next carbon, which will be part of the carbonyl group. Then, we'll add an oxygen to the carbonyl group and another oxygen to complete the carboxylic acid. Selecting the Cleanup tool will fix the bond angles and lengths. We'll save this file as a dco1.gjf. Now we're ready to use Gaussian to optimize our DCO1 molecule. Once you have your molecule ready, open Gaussian 09W. This program optimizes the structures that you create in Gauss View by running calculations using the semi-empirical method. This results in a structure with the lowest energy conformation, which can then be saved as an output file. Click File, Open, then select the GJF file that you saved in Gauss View. In percent selection, type %MEM equals 30, capital M, capital W. This sets the amount of dynamic memory used to 30 8-byte words. In route section, type pound AM1 OPT FREQ. In the title section, enter the name of your molecule. Make sure that the charge and multiplicity match your molecule. DCO1 is neutral, so its charge is 0, but if your molecule is charged, it will have to match. with -1 or 1. The multiplicity is usually 1, which indicates that all electrons are paired. In molecule specification, scroll to the bottom and delete the numbers that appear after the last dihedral angle. Then click Run. Your file will be saved as a .out file when you run your molecule. Wait for Gaussian to finish processing your molecule. This might take about a minute to complete. Look out for the message, Normal Termination of Gaussian. Once you see this message, you can exit Gaussian. After we've optimized our molecule in Gaussian, we're going to check our results. To do this, we'll open Gauss View one more time. In Gauss View, open the .out file that was generated from Gaussian. Make sure that Gaussian output files is selected in Files of Type. You can visually inspect your molecule to make sure everything looks good. Then, go to Results and click Vibrations. Make sure that the vibrations have positive values. Any negative values will appear at the top of the list, indicating an imaginary frequency. If you have a negative number, your simulation didn't find a minimum and your structure will need to be adjusted. Clicking on Start Animation will show the vibration for a selected frequency. If your values are all positive, your molecule has been successfully optimized.